Welcome to Brain Vision.
In this question, we have an infinitely deep well of width L, as can be seen in the drawing. And we have to speculate about how does the wave function changes when we change from the red reference frame to the green reference frame. So in the red reference frame, the deep well goes from x equals 0 to x equals L. And the wave function is very well known in this setup. It is given by this expression. Now, we make a translation for the green reference frame, and we have to guess what is the form of the wave function now. So we can do this by taking a look at Schrödinger's equation, because in principle, we would have to solve the equation again to get the solution, but this is not necessary. So take a look at the following. So Schrödinger's equation is written with respect to x, so it's written with respect to the red reference frame. What we have to do, all we have to do is to write it in the green reference frame and check that it doesn't change its form at all. So we can do that by following the following steps. X prime is nothing more than x minus L over 2, right? Then it's very easy to see that d dx is equals to dx prime dx times d dx prime. But we can see that dx prime dx is equals to 1, because x prime is equals to x minus a constant. So this is equals to 1, and therefore d dx is the same thing as d dx prime. So Schrödinger's equation, when written on the green reference frame, has the following form: minus h squared divided by 2m d squared psi n divided by dx prime squared, and it's equals to en psi n. So it has the same form. It doesn't change at all. It means that the solutions will also don't change. So the only thing that is changing in this setup are the boundary conditions, not the solutions themselves. Therefore, we can just make a translation in the original solution, on the solution on the red reference frame, to get the solution on the green reference frame. And we can do it as follows. We have the solution at the red reference frame right here. All we have to do is translate it to the green reference frame. How can we do that? We have to look at the relation between x and x prime, which is given by this equation. And we can see from this equation that x is equals to x prime plus L over 2. Therefore, the wave function in the green reference frame will have the following form. Psi n of x prime will be equals to the square root of 2 divided by L times the sine of n pi divided by L times x prime plus L over 2. Then we can write it as 2 divided by L times the sine of n pi x prime divided by L times n pi divided by 2 L times L. The L cancels out, and we have only this term, and that's it. And this is also in the same form of the suggestion that is given in the question. This would be the extra phase factor that appears in the suggestion. So this is what we expect for the wave function to look after the translation. Now we have to determine what are the energy values in this new reference frame. Well, it is expected that they will not change, because we are only changing the reference frame, and we are in a non-relativistic situation, and also we are using rest frames. So there is no reason to expect the energy to change at all. The energy as seen by the red frame must be the same as the energy as seen by the green frame, as both are rest frames with respect to the well. Then we can check this by making a very simple calculation, which goes as follows. So now that we have the form of the wave functions, the translated wave functions in the x prime frame, we can use Schrödinger's equation to calculate the value of En. We can use it to check that the value of En doesn't change. So d psi n over dx is equals to square root of 2 over L times the derivative of the sine is the cosine n pi x prime divided by L plus n pi over 2 times the derivative of the argument of the sine. So we get an extra factor of n pi divided by L. Now we do it again. The second derivative of psi n with respect to x prime squared is equals to n pi divided by L square root of 2 over L times the derivative of the cosine is minus sine. So minus sine of n pi x prime divided by L plus n pi times, again, an extra factor of n pi over L. So we get the following. D squared psi n divided by dx prime is equals to, this is just the psi n again, so square root of 2 over L times sine. So we repeat the wave function psi n of x prime, and then we put the extra factors, which are minus n squared pi squared divided by L squared. And then that's it. Now we plug in this result in Schrödinger's equation to get the following. Minus h squared divided by 2m times the second derivative, which is psi n of x prime times minus n squared pi squared divided by L squared is equals to the energy times psi n again. So the psi n terms cancel out, and we have the following. En is equals to n squared h squared times pi squared divided by 2m L squared. But remember that h bar is equals to h divided by 2 pi. Then h bar squared is equals to h squared divided by 4 pi squared. By replacing h bar in the expression for En by h, we get the following. En is equals to n squared times h squared times pi squared divided by 2 times 4 times pi squared times L squared. The pi factors cancel out, and we get, as expected, the same value for the energies. I forgot the mass factor here.